Let's talk now about multilayer RNNs. When we look at, let's say, a CNN, right? So we've got a CNN, we've got our image coming in, and then we've got various layers of our network. We've talked about the fact that what happens normally is we'll get low-level features at the earlier layers of the network, and then as we go into later layers of the network, that'll build up higher and higher features and more abstraction. It'd be nice to have something like that with an RNN. So with an RNN, if I enroll an RNN, so this is time step 1 up to time step t. Although these are both expanding horizontally, these are not really the same at all. So what we're doing in this RNN is continuing to just learn these kind of low-level features, because we've got the same weight matrix that we're using from time step 1 to time step 2 all the way to time step t. So in some sense, this represents really just one layer of this CNN. So we've got this corresponds to this first layer. We still might want in an RNN to be able to have these multiple layers, so we're building up more and more abstract representations. And the way to do that is really fairly simple. So we have our inputs coming in here. We of course have our H coming in here. And I'm going to call this actually H0 super 1 to represent the fact that it's at what I'm going to use as layer 1. Normally, we'd have an output coming out of here, a y-hat. But what we can do is just feed directly into now a new layer. So this is RNN1. We're going to go ahead and have RNN2 up here. And we feed the output of RNN1 into the input of RNN2. We'll have a different H sub 0. Okay, so at H sub 0 super 2, this will feed into. And if we looked out of here, we get H sub t super 2. Well, we can do this as many times as we want until we can finally end up with an RNN, let's say k, that has an input, of course, H sub 0 k. And our outputs here are our actual y-hats. So this would be y-hat sub 1, y-hat sub 2, all the way to y-hat sub t. So we're basically turning this on its side. So this is layer 1, this is layer 2, all the way up to layer k. We have our representations H we're learning here, and we're going to just feed our H's directly in an output. So as we'd seen before, we had talked before about the fact that we have an RNN, and so we have W, HH, W, XH, and W, HY. In this particular case where we're going to use multi-layers, we're actually just going to get rid of the WHY. So what we're going to feed out as the output of our RNN is we're going to directly feed out both to the right, H sub, let's say I, but also to the top, H sub I. So that H sub I at layer J becomes the input X sub I J plus 1. So that goes directly into here. So we'll be calculating the H, feeding it up in here, and then it'll go through a WXH matrix and then go into calculating the new H. Although you can construct this actually using separate RNNs, normally what happens is you actually just have a parameter to your RNN. So you will tell your RNN initialization method, how many layers am I going to have? So you might say, how many layers are going to have? Am I bidirectional or unidirectional? And that will go ahead and do the job of allocating the correct number of matrices. So for instance, if we look at WXH, we actually have a WXH super 1, which is distinct from WXH super 2, or all the way up to WXH super K. Okay. So we have got, for a single layer, a shared set of weight matrices, shared WXHs, shared WHHs, shared bias. But as we go to the new layer, it has its own distinct shared set of weight matrices and our own shared set of weight matrices. And again, if we add bidirectionality, then we're going to have, for each layer, 2 sets of weight matrices. So this is a multi-layer RNN. Just like in a regular single-layer RNN, we can compute a loss function based on the final y-hat, but we can also calculate a loss function based on any of the y-hats, any or all of the y-hats. This multi-layer construction can be used not just for RNNs, but also for LSTMs or GRUs. So if we now look at an LSTM, we would also have coming in a C sub 0 super 1, and coming out, of course, a C sub t super 1. This long-term memory would not be passed up into the higher layer. So instead, we'd still have coming out of here H sub 0 super 1, H sub 0 super 2, etc. Okay, so the C's just go straight across. The C's, as we know, always affect the hidden state, the H's, and so that's how we can pass up information from the long-term state if we need to. So we'd have C sub 0 1 coming in here, C sub 0 super 2 coming in here, C sub 0 super K coming in out here. And then we'd also have our C's. We'd also have our C's going through here as well. Okay, so H's go up, and what we should be getting is more and more complex, more and more abstract features, because of the fact that we can basically build more complex features over these simpler features that we're getting at the earlier layers. That's multi-layer RNNs.